the talk I want to give today is basically trying to kind of explain why we did this weird thing that we did as a firm, which is we adopted a deeply obscure programming language and build almost everything that we do in that sort of weird and obscure programming language. And I kind of want to talk about a little bit about why we made the decision and how we think it's turned out, and what were the kind of motivations there, and what are the both technical motivations and social motivations for doing it. So this talk is in some sense a little more prettily organized than my usual talk, because I gave a version of this talk at Google recently, so I made some actual slides. But don't let the slides put you off from raising your hand and asking questions and interrupting. I'm totally happy for this to be a conversation rather than me lecturing for a while. And in fact, I think I've given this talk a bunch of times, and I don't ever give it exactly the same way, because there's a lot of different paths you can go. So you guys already have a sense of who Jane Street is, right? So I'm not going to talk a lot about that. But I do want to talk about OCaml and kind of what kind of language that is and how it fits into the space of programming languages you might have used. I imagine you guys all have some programming experience. I feel like it's hard to be kind of a technically oriented person without have forced at some point to do a little bit of programming. So let me, just to get a sense of the room, how many of you have programmed in Java? Right? A lot. How about Python? Right? How about working in a spreadsheet? Also a form of programming. It is actually a form of programming, right? I think it's a very different form of programming, and it's kind of an interesting dual to the ordinary way we program, right? If you program in the cells of a spreadsheet, right, it's the reverse of your normal experience in programming. In programming, in ordinary languages, you see text, right, your code, that's the primary thing, and the data kind of hovers invisibly underneath. And in the spreadsheet, the relationship is reversed, right? The data is what's visible, and the code is what's hard to see. So it counts in various ways and actually ties in interesting ways to OCaml, but I won't talk much about that here. So it's worth thinking about where OCaml fits into the languages you know. So actually, let's get a little more. How many of you have programmed in Scheme? JavaScript? Haskell? Few. Okay, so there's a bunch of diversity here in the languages people have seen. I think it's worth thinking about how the programming language world breaks out and how OCaml fits in. And I'm going to kind of divide the world down two different dimensions. One dimension is the one across the top, imperative versus functional. And the other one is dynamic versus static. And here I mean dynamically typed and statically typed. And I'll talk in a little bit about what those mean. So let's just kind of go quadrant by quadrant. So in the imperative dynamic corner, you have Python and Perl and Ruby and JavaScript and PHP and languages like that. Can someone say a few words what characterizes this class? What would you call these? Scripting languages, right? And what are they like? What's good and bad programming about a scripting language?
You kind of do whatever you want, and the rules are kind of loosely enforced.
Right. Yeah, there aren't rules here, but functionally, is that good or bad? What does that mean? How does that affect the day-to-day experience of programming in them?
It's easy to write tiny things, but easy to mess up.
Right. Yeah. Right. Easy to write little programs. Right. They also tend to be pretty lightweight syntactically. Right. Not a lot of typing that needs to be done. Anything else? Any other functional properties of these languages? Slow. In some cases, crushingly, horribly, insanely slow, 100 times slower than a compiled language, right? If you Ruby or Python are both kind of amazingly slow languages. JavaScript actually shockingly good for a dynamic language because the bodies of many, many PhD students have been hurled onto a big mound to optimize JavaScript within an inch of its life. Much lipstick has been put on that pig. So now let's go to different quadrants. So static languages, C, C#, Java, C++, Fortran. Fortran is, by the way, among the very oldest programming languages and still in active use by physicists, shockingly, invented in the 50s. So what characterizes these guys? How are they different from the quadrant above?
Slower development cycle.
What's that?
Much slower development cycle.
Slower development cycle, that's right. What else? Compile. They have compilers. Anything else? Other properties are different? Closer mapping to the machine and fast, right? That's also, which aren't necessarily exactly the same, but certainly go hand in hand in many cases. So when people say a slower development cycle in part because there's this whole compiler thing you have to deal with. And also more verbose, right? There's kind of just more that has to be written down.
You tend also not to have a REPL.
Right, you tend not to have a REPL is a kind of deeply obscure piece of jargon, stands for read eval print loop. And what it means is like a little interpreter that you can like type little expressions in and see how they evaluate. And you tend to have them for languages like this and not to have them for languages like this, because these tend to have like a big heavyweight, like compile everything and then run it kind of model. So what's the dimension on which these guys differ? They differ on the dimension of how the type system works. So first of all, just to say for a second, what is a type system for? What are types? So when you think about programming, there are all these objects floating around in your program, values that you're dealing with, and you can categorize these into classes. And in some sense, you can call those types, right? There are different types of values. There's another thing in your program, which is a little bit more abstract, which is the idea of a variable, right? What's a variable? A variable is a name that points to some value, right? A variable isn't a concrete thing necessarily that points to a concrete spot in memory in a unique way at all times. It's just a name in your program, a logical name for things, which is similar in many ways to like a name in an equation, right? You know, you name your variables in an equation and you name your variables in your program. Those things are in many ways very similar to each other. So in a dynamically typed language, values have types because there are different kinds of things your language deals with, but variables don't. In a statically typed language, the variables themselves also have types, which is to say, at the time your program is written, the compiler can do a kind of static analysis. It can look at your code and say, oh, this variable always refers to things of a certain type. Right? And so why is that important? So there are really two different reasons it's important. One reason it's important is because of speed. Right? And the reason it matters for speed is if you know in advance what are the kinds of things that are being manipulated, then you can write extremely efficient code for doing that. So in a compiled language, if you add together two integers, what that turns into at runtime is effectively a single machine instruction that says, you know, add the contents of this register to the contents of that register and put it in the other register, right? A single instruction. If you go to a dynamically typed language like Ruby, it's a sort of longer conversation that starts, oh, you want to add things together. Well, what are the things, right? Maybe they're strings and I should concatenate them, and maybe they're integers and then I should add them together. Or maybe they're floating point numbers and I need a different routine for adding them together. Or maybe they're two integers and I'll add them together and now they don't fit anymore in what a kind of normal machine integer is. And so I need to use a big num. Like, there's all sorts of complicated things that can happen in a dynamic language, and it's in that gap of figuring out what you need to do. That's where the factor of 100 tends to come in.
Fair, I've seen code that looks frighteningly like that in Java.
You're saying machine code that looks like that?
Statically typed imperative code that goes, oh, hey, you don't add. Well, what are you adding? Let's introspect all these types for half an hour and then decide whether to do it.
That's right. So I guess one thing to say about all of this categorization is that none of it is precise. Right? So, for example, this kind of runtime decisions about what you're going to do, that's the dominant way that things work in dynamic languages. But there are parts of static languages that operate that way. For example, lots of statically typed languages, Java included, offer forms of introspection, which is like a language feature that lets you kind of ask questions about the type and make decisions about it, and is also crushingly slow in the way that dynamic languages, I think probably even slower than most dynamic languages are. So yeah, there are things on the boundary that don't quite work, and we'll see actually more of that as we move to the right-hand side. I guess another thing to note about this whole column of languages is they're all fairly popular, right? So in a second we're going to get to the unpopular side of the street. Oh, and so I said performance. I said performance a bunch of times about types. There's also correctness. So types were really born for performance. If you go back to the 50s when people were first inventing programming languages, there were really two major languages. There was Lisp and there was Fortran. Right? There was a few other things invented back then, but like the only things that had any staying power were those two languages. And Lisp, we'll see, was actually in the functional dynamic corner, and Fortran was in the static imperative corner. And I think the key reason why Fortran was static was because they needed to be really fast because they were running, big jobs with lots of matrix operations for computing various physics simulations. And so the types were necessary for that. But types are also useful for making your code more correct, for helping you nail down properties of your program more reliably. And I'm going to talk a little bit more about how that works, but it's just worth knowing as kind of background that that's an important part of the distinction between these two classes. OK, so there's functional dynamic languages. And you see we have gone off the cliff in popularity already. Lisp, Scheme, Racket, Clojure. Again, you could decide to take JavaScript and kind of squish it over to the functional side. This goes to the fuzzy separation between different kinds of languages. In many cases, whether something is a functional language is some mix of what language features does it have and how does it tend to be used. So now that I've listed some languages, maybe it's worth saying what does it mean when you say functional versus imperative? And there are kind of two things that come up in this distinction. One part of being a functional language is having good support for programming with functions as a kind of lightweight and simple abstraction. One thing that you get in all of these languages on the right-hand side are functions are things that are easy and lightweight to create, and you can deal with them as if they were data. Right? You can take a function and pass it as an argument to another function and have that return another function and take a function and store it in a table of functions. You can, in a very easy way, kind of fling functions around. And that's one thing that characterizes the class. The other thing is that functional languages give you good support for programming in what's called a pure style of programming. And the term purity is itself, I think, sort of a little tendentious. It's like, well, it must be good. It's pure, right? But pure means something kind of with less inherent values in it than the name sounds like. Pure means programming that doesn't involve mutation, that doesn't involve changing the values of things as your program evolves. And I think to someone who hasn't programmed in a functional environment, that seems kind of weird. How do you compute something? You always compute things by, you have some data and you compute some things and you modify what you had before, and you do that over and over in a loop until you get the right value, and then you're done, right? It's just sort of the ordinary way that you compute. And it turns out that's not the only way to express a computation. It's not the only way to do it. And just to give a kind of concrete sense of that, let's get to the terrible part of the talk where I actually bring up code. So just a really simple example. So here is a simple function for summing a list in Python. And this, like lots of programs you've probably written, is done in an imperative style and is pretty simple, right? So we want to sum everything in the list. We initialize a variable total to 0, and then we have a for loop that goes over all the elements in the list and increments the total by that number, and then we return the total. Right? So does anyone have questions? This is meant to be pretty straightforward. OK, so now, let me actually make this a touch smaller. So here is the corresponding function in OCaml, which is a functional language, as we'll see. So this syntax is going to be somewhat foreign for those of you who haven't programmed in OCaml or Haskell. Or a similar language, but let me just kind of walk through. So this whole let rec sum of list just means declare a function that has a single argument list. The rec here means the function is going to be recursive, meaning the function is allowed to call itself. And we look at the list and we see which case we're in, and we say if we're in the case of an empty list, we're going to return 0. And if we're in the case of a list that has at least one element called first, and some remainder of the list called rest, then we're going to return first plus the sum of the rest. Right? So I guess one interesting question is, which of these seems more natural and intuitive to you? Raise your hand if the Python one seems like the more natural one. Really, only that? Not everyone? I feel like even to me, who's about as addled by these languages as possible, this one still seems a little bit easier to follow. Right? This one is the recursive definition, right? This is kind of, if you were doing an axiomatic description of of what does it mean to sum the elements of a list, you might write it this way with this kind of recurrence relation. But it's a little bit of an odd way to write down a summation, at least I think. But it does have a certain clean mathematical flavor to it. And it's worth noting, it doesn't have any notion of mutation, right? Nowhere is there a variable which has a value and we say, and now we're going to change the value. So there's a thing that often confuses people about functional languages, which is in functional languages, you have these things called variables, but they don't exactly vary in the way that you might expect them to, right? You don't modify this within them, so why do you call them variables? And the reason is you call them variables for the same reason you call variables and equations variables. Not that it varies over the course of executing the equation, right? It's because the equation can be applied to many different inputs, right? There's some part of the equation which is like static, and some part of it that you can think of as varying over the different possible applications. And that's what's going on here, right? We can call sum on many different lists. So, and indeed, sum calls itself. So over the course of the many different executions of this sum function, first will mean different things at different times. But we were able to write it down in a way that doesn't explicitly do anything that looks like mutation. So I think one obvious question about this is who the hell cares? Right? Why does the distinction between two different styles matter? And I think the reason it matters is because mutation is more than just a way of getting a computation done. Right? So the mutation here is in some sense very simple and importantly very local. Right? There's this little tiny function which mints a new mutable variable in some very small scope, and it never escapes anywhere else, and it kind of runs for a while and then finishes, and like the mutation is all kind of contained in a little tiny box. But in general, when you have a mutable state in your program, when you have stuff that can be mutated, that mutable state, that changeable state, is more than just a way of computing things. It's a communication channel. It is a way for different parts of your program to talk to each other. And the reason you want to avoid that, when you can, is that having a program that is cleanly separable into different pieces that don't talk to each other is really valuable for having a program that's easy to reason about as you compose it together, right? It's nice to be able to have different parts of your program that may be running kind of together as part of one massive system that you're building, and to be able to think about the program that you've built by assembling these together as a kind of simple composition of the pieces that you started with. And the more mutation that you have in your program, the harder that is to do, because that mutation gives different kind of back channels for different parts of your program to talk to each other. Whereas when you're in a functional setting where you're not mutating anything, and the only form of variation is like the functions being called on different values, then the functions are really explicit about what their inputs are and what their outputs are, and it's easy to understand how the pieces connect to each other. So in some sense, thinking about these examples in the small gives you the wrong intuition, because it's not the examples in the small that make avoiding side effects useful. It's also worth saying that there's nothing wrong with side effects. It's nothing wrong. Side effects is about another technical term for mutation and other similar things. There's nothing actually wrong with doing that in your program. In fact, all interesting programs have side effects, right? You write your program because you want to have some effect on the world. Otherwise, it's a kind of a boring thing to do, right? And very few programs can be thought of as just like pure computations that, like, you give them some input and they produce some output. That's all they do. Programs read things from file systems and look at the clock and write stuff to the network, right? In the end, almost all real-world programming is about having an effect on the world. So you should judge your functional programming language, and any programming language, not so much on how much it lets you program without effects, but how much it helps you program with effects. And the reason why it's good to have the ability in the language to program in this way without effects is because that part of the program, the part that doesn't have effects, is simpler to reason about, simpler to think about. And maximizing the amount of your program that's easy to reason about is good. But it's not like you're trying to ban effects from your program, right? That's sort of at the heart of what you want to do. So there's a lot of really abstract stuff here. Does anyone want to ask any questions about this part? Please.
When you're running this, does your program have to remember sort of that once it sums the rest, it will then have to go back and sum first, or it keeps a chain of like, but it's 1,000 long, it seems like 1,040.
Right. Right. So it does. So I wrote this program I wrote this little function in the simplest way possible, which has this property of, for for those of you who know a little bit more about how programming languages work, it allocates one stack frame per element on the list. But there's a small transformation you can do to have a recursive function that doesn't have that property. But I wanted to maximize in this example for readability rather than performance.
So you mentioned that like the advantage is that it's easier to like compose and program. But that's also like the point of having like C++ and classes, like object-oriented stuff. How is this actually better than having like an object-based approach?
So it's different in a lot of ways, but there are two orthogonal things you can do in your programming language that make composition easier. One is to have good forms of abstraction. And objects give you a form of abstraction. I think not quite as good as the one you get in a language like ML. That's a more complicated story that probably is outside of the scope of this talk. But it gives you that. But having effects in your language has communication channels that get added in a fundamental way, right? And like, you don't have to trust me. Like John Carmack, right? Raise your hand if you know who John Carmack is. Okay, raise your hand if you've played like Quake or Rage or Doom or have ever heard of those games. Oh, wow, it's been a while, I guess. So John Carmack is an excellent C++ programmer, one of like kind of a fairly legendary guy in the games industry. He's done lots and lots and lots of hacking in C++. And if you listen to the way he talks about programming, he argues very strongly in favor of immutability, right? Avoiding effects as a way of making your programs easier to decompose. This is, I think, fairly standard advice for people building programs in almost any language. Or like, go read the book Effective Java by Josh Block, who was like chief Java engineer at Sun, right? Like, immutability simplifies things because I can have some nicely encapsulated object, but like if this part of the program modifies that object and this part of the program reads from that object, like it's lovely that you put an abstraction barrier around it, but these two things now are still having this kind of communication channel between each other, which is not explicit anywhere in the code, right? Like this guy doesn't know that this guy exists and kind of has no way of knowing about it. So composability is about more than just avoiding mutation, but mutation does give you a bunch of value of that kind. Another example to think about is concurrency, right? Races are really hard to think about in the context of mutable data and basically trivial in the absence of it, right? Because the lack of mutation means there's no interference when things are interleaved with each other. Okay? All right, so I'm going to go back to the slides. Right, so now we've gotten to the last. I think this used to be the most unpopular corner of this slide, and I think over time it's gotten a little more equalized with the one directly above it. So OCaml is the one we use. Scala is a pretty well-known language in the same rough family that runs on the JVM. Haskell is in many ways quite similar to OCaml. F# is an OCaml clone that runs on the .NET version, and SML is a language really, really similar to OCaml that kind of comes out of the same kind of historical line of research from which OCaml came. So this adds to this basic functional set of ideas of functional programming, adds these static types that you are used to from languages like C, C#, and Java. But interestingly, the type systems that these languages in the bottom right-hand corner have are actually a lot better and more powerful than the type systems you tend to have on the systems on the left. And I think it's in some sense accidental. Like, I don't think it had to be the fact that the ones on the right are functional languages and have these more sophisticated type systems wasn't a necessary property. I think one of the reasons why it happened this way is the ones on this side tend to be object-oriented languages. And object orientation is actually a lot harder to get right in terms of figuring out what's a reasonable way of mapping it onto a good type system. It's just a lot more complicated. And so in some sense, the problems were simpler over here, and so people were able to build nicer and fancier type systems. But one of the key trade-offs that you had between dynamic and static over here, you don't have when going to the functional static side, which is functional static languages tend to be fast at about the same level as the imperative languages. But you don't have the same syntactic overhead. And in fact, we can go back to that example we just looked at. And like, so if you've programmed in Java, think how long the Java version of this would look like. Like it would look a lot longer, right? And here, this is statically typed, I said, right? But why should you believe me, right? Well, I can ask. Comes off really small, unfortunately. But I went over here and asked the editor to tell me what type it was. And it says, oh, it's an integer list arrow int. So a function that takes an integer list and returns an int, right? I can't do that in the Python side because Python doesn't know. Right? It has no way of knowing what the types are. But OCaml knows the types of things by a process called type inference, which is to say it kind of looks at the program and says, well, what type does it seem like this has to be? So it says, well, let's say you matched a list with this pattern. That pattern turns out to only apply to lists. So this thing that you called list is also of type list with something on the inside. What might be on the inside? Well, I've plussed things together. Plus is an operator on integers, so it must be integers, and now you know the input is an integer list. And because we return 0 here, so this thing must return an integer list as well. Or sorry, must return an integer. So basically, type inference is a process which takes the little hints that you get from the program as to what things are doing and infers the overall types. And there's a trade-off here. It gives you a lot of extra concision. Things are much tighter at a syntactic level. It's also a little more complicated to understand, especially when it goes wrong. Like the type errors are not super hot in all cases, right? It can be pretty confusing. But overall, I think of this as a pretty big win. And in fact, if you look overall at how programming languages are evolving, type inference is becoming more and more popular. Languages like C# are getting local type inference as a kind of addition to the language. Okay, so that was a lot of really kind of high-level stuff about programming languages and where they fit in. Let me talk a little bit about why we care about this. So we ended up switching to OCaml a long time ago. About around a decade ago was kind of when we started using it for the kind of primary development language for building new systems. And there's a bunch of interesting reasons that went into that. Some of them actually had to do with non-technical things, like how easy it was to hire people. And it turned out it was easier for us to hire people from the empty set of OCaml programmers than from the very large set of Java programmers, say. And that's in part because even though the set of OCaml programmers is empty, the people in that set are pretty good. And I guess it's a set of measure 0, more precisely. But technically, why do we think these languages are good? And I think if you think about what distinguishes the business we do, one of the key properties is it's terrifying, right? I mean, for all of those of you who have programmed, you are, of course, terrible at it. Right? We all are. Humans are really bad at programming. Like you write programs, and they're full of bugs, and they don't come out very well. And one of the things you learn after having done it for a long time is you don't get that much better. I mean, you get better, but you're still like full of errors and mistakes all the time. And going and writing programs that you then like let loose on the markets and have access to your wallet, like that's kind of terrifying. And if it's not terrifying to you, you haven't thought about it enough. And so we care a lot about having things that help us write programs that don't do the wrong thing, that do what we expect, that behave in ways that we can understand. And there's lots of ways of getting there. Testing is, of course, an important way of getting confidence about the programs that you write. But there are things about the financial markets that make testing not like the only story you want to tell. One of them is that financial distributions tend to be tail-heavy, which is to say things happen rarely, but less rarely than you might think, that are really dramatic. Right? Think sort of, if you just kind of say, things happen kind of in a normal distribution, things far out are like, decreasing probably very, very fast. And so like I can pretty quickly cover the territory I want to cover by just random sampling. And like, for complex programs with large spaces of possible things that can happen, even that's not a very good story. But like in the financial markets, it's especially bad because things can vary, by orders of magnitude more than you might expect if you thought things were normally distributed. So that's kind of one kind of sort of high-level reason why testing isn't quite the full story that you want. The other thing is there's an adversary, right? A thing to remember about trading is like overall, trading is a positive expectancy business, like for the people participating in it and for the world, right? When you trade, you're acting as an intermediary. Other people's transactions are, cheaper and easier to do because you're there being on the other side. But on any individual trade, right, as you turn the dial to the right, say, I'm making more and more money, right? Somewhere else is a dial being turned to the left, right? And someone might not want you to turn that dial, right? And someone might want to turn the dial the other way on you, right? So like you can test against what you think is going on, but you kind of want, in some sense, for the more mathematically inclined, you want the power of the upside down A, right? Universal quantification. For all cases, you want to know about properties for all cases. And testing is a way of approximating that, but if you can get some of these, some of that universal guarantees in other ways, it's really valuable. And one way is by reading and understanding the code. But we're all very bad at that, right? Like it's an important thing to do, but there's lots and lots of mistakes that humans make, and having tools that help catch those mistakes for you is worth a lot. And type systems turn out to be a very good tool for catching a surprising number of mistakes. So it's very hard to really give you a flavor for this kind of in the context of a short talk, right? I can give you a few examples, and there's only kind of limited, they can only have limited kind of convincing power. So I'm going to give you a few examples, but if you really want to understand this well, you have to actually go and use it, right? There's I know stories of people who've for years heard about people talking about how useful OCaml and ML's type system is. And like, yeah, it's fine. I guess it's somewhat helpful. And then they go and use it, and they're like, oh no, it's really true, right? Like, it used to be, I'd write a program and then spend a lot of time debugging it. And now I write a program and like a whole class of trivial bugs just aren't there. Right? It's a surprisingly dramatic effect. So I'm not going to be able to kind of show that effect in full force, but let me try and show you a little bit of how this kind of works out. Let's see. So let's start with this example. So here's a small piece of Python code. So the idea is you're supposed to, this is a function that is supposed to take as input two dictionaries, where dictionaries are mappings from key to data, and find all the keys that are in both dictionaries whose data differs, right? So look at this piece of code for a second and see if you can tell me anything interesting about it.
If the key is in a D2 your data.
Right. So if the key is, so if what's that?
For Python dictionary lookups, if the key doesn't exist, does it return none? Or I think it's an error.
In this case, it throws an exception, it turns out. But like in Lua, it'll return null, right? It depends exactly which language you're in, but in Python, it throws an exception, right? So there's a bug, not a very complicated bug, a pretty simple bug here. But it's the kind of bug that humans make all the time, right? This is, again, someone asked, is that an exception or a null? So it could be either one. So you can pick your poison. Is your program going to crash with an exception that's generated by this lookup, or is it going to crash with a null pointer exception? But like the difference isn't all that exciting. In both cases, it's going to crash when you run it. And this is, of course, the good outcome. The bad outcome is if you're in a language where D2 of key returns null, and then this just does the wrong thing, right? It's just it's like, it just checks against whether it's null, and right? It's sort of not, it's like a case that's handled automatically and you weren't really thinking about it, and maybe it got handled the wrong way, or maybe it got handled the right way. It's kind of ugly. So, sorry. So now let's look at what the same thing might look like in OCaml. So there's a bunch of obscure characters here that you won't recognize. So let me kind of walk you through the part that really matters. Here we take, so these things that you call dictionaries in Python, we call more or less the same thing, maps in OCaml. Here we take the map and convert it to a sequence, which just means we're going to think about the set of key value pairs. And then we're going to call this function filter map, which is going to iterate over everything in the dictionary. And it will allow you to return either none or some of something. So this is a thing that's in the type system in OCaml that just isn't in the type system in Java or C# or C++, called a variant, where there are two different cases, and it lets you kind of return into one data type these two different possibilities. And then if you return none, then it will drop that thing from the return sequence, and if you return some of something, it will return the object inside the sum tag. So it's probably still a little obscure. Let's walk through a little more here. So we call this function map.find of map2 and the key. So remember, this key, like the key up here, this is the key from the first dictionary /map. And again, this is the key from the first one because we've filter mapped over, we filter mapped over the data in map 1. So key comes from map 1. And then we're going to look up using this map.find function in map 2. And then the reason we did a match is because there are two possible cases, either none or some. So in the none case, which sort of corresponds to null, as we were thinking about before, well, it returns, we're going to return none, meaning we're going to drop it in the case that it's not in the second list. And if there is some data, then we're going to say if the data is different, if the data in the second map is different from the data in the first map, then we'll keep the key in the returned list, and otherwise we won't. And so one thing you might look at this code and say, well, why is this different from the Python code, right? Maybe you could have explicitly handled the case of the thing not being in the second map there too, and then it would have also been correct. But the difference is the way we've written like our libraries, the way map.find works, because it returns this explicit none or some type, which is called an option type, you actually can't ignore it. Meaning if you try and ignore it, the compiler will just yell at you and say, like, no, it doesn't work. It will just fail to compile. The compiler essentially forces you to do the case analysis, right? And this goes to the question before of like, we were talking about like what's different between a typed and an untyped language. In an untyped language, you can kind of do whatever you want, and in a typed language, there's a bunch of constraints. And this is an example of the constraint. We were able to design our map library in a way that it imposes obligations on the users of the library to do case analysis. And those kind of obligations are really valuable for improving the quality of your code base, right? They help you track down bugs and make sure that things are handled in the way that they should be handled. When people first encounter type systems and the distinction between languages with type system and languages without them, I think their attitude is often one of like, maybe it's good and maybe it's not. Like, there's a type system and it catches some bugs for me, and that's nice. And then it also stops me from doing some things that I want to do, and maybe that's not so nice. And so, you can sort of think of like the type system as like a nanny that hovers on top of your code and slaps your hand when you do the wrong thing. But this is sort of an impoverished view of what types are useful for, because really, types should be part of your design process, because you want your program to be right? You want it to be correct, and you need to do a lot of work. Whatever programming systems you're using, you need to do a lot of work to try and ensure that your program is right. Maybe it's writing a lot of tests. Maybe it's writing the code so it's really simple for humans to read. Maybe it's using the type system. But these are all tools that you use actively in the design to make things less error-prone. And if you just think of types as like a nanny that sits on the outside and catches when you pass in an integer when you meant to pass in a string, that's kind of all it will do for you. But if you actively design your program with types in mind, you can drive error rates down a lot more. Let me give another little example about types. This is sort of an unfair example, but I want to give a sense of why, how type systems affect how easy it is to write code. I think type systems kind of get a bad name in some sense because of languages like Java, where the type system imposes a lot of verbosity. So just to kind of give a concrete example, here is, it's a little bit of an unfair example because it's right in the wheelhouse of what OCaml does really well. But here is a very simple piece of code for expressing a binary, a kind of Boolean expression language. Right? So imagine you want to like have, say, a filter that you think about like the Gmail filters you write, where you say like, I want all messages that have, have this and that, or the other thing, but not this, right? So you want like some set of Boolean operators that you want to smash together for this. And then at the bottom, there's some set of base predicates like, this regular expression shows up in this email, or the from line, and it is from this person. Right? So the idea here is this type we introduce here is an alpha expression, meaning that alpha is what's called a type variable, the tick A, right? I don't know, why am I suddenly in Greek, right? The tick A there is a type variable, which means that this is a general class of types. So we're going to be able to have these kind of Boolean expressions used for filters for emails, or we could use them for filters for our traffic viewers upstairs, or whatever. You can use it for lots of different things. It's generic. This is actually, that tick A is like the generics you see in Java. So like the angle bracket A, angle bracket. It's the same basic concept, if that helps. So here, this is a little bit like the none and some case. There are a few different possibilities for the type. True, false, and or not, and then the last one is base. And that corresponds to these base predicates that we're going to be kind of weaving together inside these expressions. And then here I have a little function whose job is to evaluate an expression. So this is like super simple. So there's this eval function that takes as an argument a function called eval base. And so this is the thing that evaluates base predicates. And it takes the expression you want to evaluate. And then all this code is going to sort of is the guts of that evaluation. And by the way, where you immediately see the sort of first class use of functions here as well, right? Eval base is a function that gets passed into eval. And in fact, we can ask what the type of that function is. And it's alpha to bool. And in fact, the overall type of eval is it takes a function that takes alpha, which is going to be the type of the base predicate, and to true or false, and an alpha expression, and returns a single true or false for the overall expression. If you have questions about this so far, I'm going to go into this code, but I want to make sure people have some understanding.
Sorry, so I'm confused by the two arrows. So it takes a function to.
Oh, yeah, this is a terrible bit of sort of syntactic nonsense. Just when you have a collection of arrows like this, think of this as a function with two arguments, where this is the type of the first argument, and this is the type of the second argument, and then the first argument is itself a function. There's some interesting technical reason why it's written in that odd way. It's not actually a good idea, it turns out, but that's how it works. Sorry, did you have a question?
Probably just ask you afterwards. It's sort of a dumb question. I just don't understand what you're saying by a base predicate, but I haven't taken much comp sci, so I don't know if that's just a...
No, I think the right assumption is if you don't understand it, like 60% of the room also doesn't understand it. So what I mean is, if I want to be able to say, I want all the messages that are from Microsoft.com and have the subject line virus, right? Well, you can think of that as a conjunction, like and, just a logical conjunction, this and that, right? So just you think about like in ordinary math, right? There's like Boolean logic, right? But it doesn't tell you what the subject matter is. It just says, oh, this is what an and is, and this is what an or is, and this is what implication means. But in the end, to have a useful system out of this, you have to have facts about the world. And the base predicates are the facts about the world, right? So the idea is this is like a little language for pulling together a bunch of facts that you know about the world and constructing an expression that talks about how those facts relate to each other.
When I see alpha expression, do I think of it as an expression with type parameter alpha?
Yes, alpha expression, that's right. That's exactly right. All right, so what does this code do? So we actually defined another function called eval prime, which is basically just a specialized version of eval that already knows about eval base. If that doesn't make sense, don't worry about it. Just think of it as just calling eval. And then we do a pattern match. We look at the expression and say, what are the possibilities? If it's the case we call true, then we return the Boolean value true. If it was the one we called false, we return the Boolean value false. If it's a base predicate, we call eval base on that predicate. If it's and of two things, well, then we eval the first one and do the ordinary logical conjunction with the eval of the second one. If it's or, we do a disjunction. And if it's not, we do the negation in the language. We just kind of here very straightforwardly translated all these things in our little language into the corresponding operations in OCaml's libraries. Right? So the code is, in some sense, more than anything else, really boring. Right? It's like and is and or is or, and true is true, and false is false. Like there's almost nothing there, right? Which is kind of how it should be. Here's the Java version. It's probably not worth going into great detail on this code base and exactly what it's doing. Like you see, it has the same. Like I tried to map the structure pretty closely. Sorry, I'm trying to get everything to fit. So that angle bracket t angle bracket is that same parameterization over what the input is. But I think a thing to note about this is the reason it's so much more verbose is there's some accidental details of Java's design which are just not so great that make it more verbose than it needs to be. But a big part of why it's verbose is it's missing something in the type system. It doesn't, this whole thing where there's a variant with a bunch of different cases and that you want to kind of match on them and make sure you cover all of them and all that, it's just not naturally expressed in Java. it's just kind of a hard thing to say concisely. And so this goes to the other reason why the type system in OCaml is very useful. One is, I said before, it helps you catch lots of bugs. But the other is, it's more precise, it's more expressive. You can say more of what you want to say about your programs in the type system than you can in more traditional languages. Right? And there's actually lots of examples. This is a somewhat the equals, right? This is, I think now they're at the same font size. This is again, it's a little bit of an unfair example, but it's not that unfair. In fact, I think in many cases, a 3-to-1 compression ratio between Java and ML is not that unusual, and a lot of it has to do with the details of the type system. Does this make sense to people? Any other questions about it? So there's a lot more to say about types and why they're valuable, and I'll say a little bit more about that along the way. But let me move to another thing about ML that I think turns out to be very useful, which has to do with what I like to call the dynamic range of the language. So there's a common thing you'll hear programmers say, which is you should pick the right tool for the job. Right? If you're doing a little scripting job, you should write it in Bash or Python or Ruby. If you're doing, a big, complicated enterprise program, you should write it in something like Java. If it's a close to the middle, this or that, you should write it in C++, and whatever. People have a pretty strong view that you should use different tools for different kinds of applications, for different kinds of problems you're trying to solve. And this is, in some sense, obviously true. You should, of course, pick the right tool for the job. Who is going to recommend to pick the wrong tool for the job, right? But there's something behind this suggestion, which is, it's not just saying you should pick the right tool for the job. It's saying you need a really big tool set with lots of different choices to handle all the different kinds of jobs you have. And I think, to some degree, that perspective comes from the fact that people's normal tools suck, right? They don't have good dynamic range. They're not good for a wide range of problems. And this goes back to the thing that I think is really nice about this class of languages that OCaml sits in, is it's in a kind of sweet spot in the design space. It is concise, like traditional dynamic languages are, and efficient on the scale that traditional compiled languages are. It has a type system that catches lots of errors for you and doesn't require a lot of typing to get in place, and is relatively easy to work with. I think that if you look at the design of programming languages, there's lots of things that you can do to get even stronger guarantees and even more precise kind of help from the compiler in catching bugs. But as you push more and more in that direction, it gets kind of more and more complicated to use. And OCaml happens to kind of sit in a nice place where it's both really good at catching bugs and relatively simple to understand what it's doing. I guess to people who are learning it for the first time, it maybe doesn't feel enormously simple to understand, but maybe that's just by comparison. And I think that this is reflected a lot in our own use of the language. We use OCaml for everything from little scripts that we're running to just automate small tasks to kind of lightweight kind of mini languages for writing config files, all the way to kind of big trading systems that we, trade billions of dollars a day through. And one of the advantages in an organization like this of having a single tool that works for a wide variety of applications is you get to share a lot. One thing that's notable about us is we're a pretty small organization, right? I think we have, somewhere north of 400 employees now, something like 70 full-time developers, maybe another 50 to 100 people who spend a significant fraction of their day programming in one form or another. But I don't know, Twitter has 2,000 programmers, and that's, their main product is Twitter, right? That's, it's not like Google is of enormous scale and does lots of different things, but even for a project that feels to the outside like a relatively small thing, right? there's a lot of humans working on it. We have a really small set of people working on a pretty big and complicated infrastructure, and you really want to maximize people's individual productivity, their ability to do things and both get things done in one area where they're in and also be able to switch to some other area. Like one terrible thing that can happen to you is like you use some obscure tool that the rest of the company doesn't use in some area to build something, and then nobody else wants to touch it ever. And you're kind of chained to it, till the project kind of dies and withers away. And the fact that we have one tool that we use for a very broad set of things makes it easier to kind of share ideas and share code and share people across that. And that's all very valuable for making people more productive. Let me skip this slide. Yeah, so I want to talk about, the hackability thing is interesting, but we're super running out of time at this point. So teaching. So one of the questions that comes up when you think about using some weird, obscure, academically well-liked programming language is, like, can you actually effectively teach people it? And this is not a rare concern when thinking about new programming languages. And there's a great quote by Rob Pike, who's at Google, and he is the author of Go, which is a programming language you guys may have heard of, which is one of the few new languages at Google. Google is actually very restrictive in what language they let people use. They have like basically 3 blessed languages, I think C, C++, and Java. No, it's like C++, Java, and Python, sorry. I think are their 3 blessed languages, and C++ kind of includes C as a sub-language. And in addition, they now have Go as a language that people use for doing some production stuff. And so Pike says, well, the key point here is our programmers are Googlers. They're not researchers. They're typically fairly young, fresh out of school, probably learned Java, maybe learned C or C++, probably learned Python. They're not capable of understanding a brilliant language. But we want to use them to build good software. So the language that we give them has to be easy for them to understand and easy to adopt. This is, by the way, a great slide to give it when I gave the talk at Google. It's fun. So I feel like Pike's phrasing is a little condescending and unfortunate to the people at Google. But the point is super reasonable, right? Like when he says, they're not capable of understanding a brilliant language, that's not a compliment, right? Like this, brilliant in the bad way of you have to be brilliant to understand it, right? This is not a property you want of your tools, right? So it leads to the question of like, is OCaml too hard? Is it a brilliant language in the bad sense of the word brilliant? And it's hard to definitively answer the question. I mean, I think in some sense, from our internal perspective, clearly not, in the sense that we have lots of people here who successfully program in OCaml. But there's lots of selection involved there, right? One of the ways we attract people here is people who have an unhealthy interest in functional programming are more likely to come and want to work here. And so maybe we're really bad at telling whether or not this is a kind of language that's really too hard for general purpose use. My intuition is that it's not, and I think there are some bits of evidence that lean me in the direction of thinking it's not really too hard to understand. One is we actually have all the traders learn how to program in OCaml some. So there's an OCaml bootcamp where people do, so this is largely for the traders. Some people from other parts of the firm, compliance and operations often do it as well. But the bulk of people are people on the trading side. And it is a month-long program where people kind of are all off sitting with each other, learning the Unix shell and Emacs and OCaml and our build system and all of our libraries and how to use a monad, and it's a complicated thing of its own that I won't really discuss. And it's not too bad. I feel like about half the people get over the finish line where they are then able to go and do useful things. And the other half of the people, I think, come out a little more informed and less afraid of various of the tools, but not actually going and using it for useful stuff. But that's one example where we can take a pretty broad class of people in a kind of stunningly short period of time and get them to a level of reasonable competence without enormous amounts of difficulty. Another experience that we've had is we have a Wintern program where we've had people come in. We have for basically mostly MIT and Harvard and sometimes Brown have winter breaks that are aligned nicely so that we can have people come and do a short internship here. And it's really short. It's I think for the Harvard students, it's 3 weeks, and the MIT students, it's 4 weeks. And interestingly, the difference between the Harvard and the MIT students is the Harvard students have all learned OCaml because it turns out it's part of the kind of standard curriculum there. There's intro CS class, part of that sequence is in OCaml, and the MIT students don't. And by the end, with that extra week, they're all kind of able to like put together a simple project. So that all gives me some hope on the question of whether it is, a brilliant language in that sense. But again, it's hard. There's lots of ways in which the experience here is limited. But at least my feeling from it in our experience is that I think it's not too painfully hard. So another interesting bit, hiring, right? So I mentioned this earlier in the talk, how hiring turns out to work pretty well. And this is an interesting quote from an essay that Paul Graham wrote years ago. So Paul Graham, if you haven't heard of him, he's the guy behind Y Combinator, which is this startup angel, it's like startup camp, right? So he wrote in an essay a long time ago called The Python Paradox about how picking an esoteric language allows you to attract better programmers. It's interesting, actually, that he wrote this more than a decade ago about Python, where then Python was an esoteric language, and now knowing Python is like evidence that you can breathe. But other than that, little else. And I'd say this has been a quite useful effect for us, and there are two parts of it. One effect is there's selecting people who are good to come work here. And that definitely is an effect, right? This thing of saying the average OCaml programmer is pretty good even though there aren't any of them. That totally worked out for us. One of our early rounds of hiring, I sent one email to the OCaml mailing list. I got 15 responses, of which 12 seemed worth responding, of which 5 were worth bringing in on-sites, of which 3 we made offers to and hired, and they were really good, right? And that is a shockingly good sort of work to reward ratio. But over time, actually, the value of the effect has shifted almost entirely the other way, which is we now talk to many more people and look at lots more resumes. And now I think the overwhelming effect is not that it helps us find people who are good, but it causes people who are good to have a reason to come work here, right? I think that if you come out with a computer science degree and think, what am I going to go do with my life? It's like, well, where do other computer science people go? It's not so much to finance, right? It's to optimizing the delivery of ads or something, right? It's been decided that some other area is the area where computer scientists go for reasons that to some degree escape me. But having an unusual technical choice that you've made that is attractive to a subset of people turns out to be really effective for attracting people. There are lots of people who would never have spoken to us, but we got to hire them. Like Stephen Weeks is an example I could bring up. He is the author of the world's kind of fastest ML compiler, or maybe actually the world's slowest ML compiler that generates the fastest code. But anyway, and there's absolutely no way he would work here but for the choice of the technology. And he's really good. And there's a lot of people like that who we have here only because of this. So I think there's lots of confounding effects in the world where you think picking some technology will kind of box you out and make it hard to hire people, but sometimes it goes the other way despite the way the numbers work out. So this is a thing worth saying, which this is like a real bad side of using a minority language. Not so much about the language, but about just using a deeply unpopular language, any deeply unpopular language, which is the tools are no good, and there aren't that many libraries. And I think from our perspective, it wasn't so bad initially because we had lots of things we needed to build that were completely custom. If we were doing web development, I think it would have been a very different story. There's lots of oh my God, you don't want to reinvent all of those wheels. There's a lot of wheels involved in getting all the web browsers to obey your will in the way that they need to obey your will and hooking into the databases. And there's just lots of things you don't want to have to reinvent. And we didn't have as much of that issue. But it still hurts. And I think it's an ongoing problem and one we've tried to work on by trying in various ways to help kind of OCaml and the community get more popular and help support in ways monetary and others, things in the tools that make things better. There's actually been a huge amount of progress in this way. OPAM is a package management system for OCaml, which, unlike all the other ones that preceded it, doesn't completely suck. It's actually pretty good. There's Merlin, which actually Fred, who's sitting over there, is one of the main authors of, and Thomas Rafi, who works here, have done, which is a kind of kind of like IntelliSense-like auto-completion and looking up of types and things like that, which is awesome. OCP Indent is another small tool for automating the indentation of your code, kind of like Go Format, if you've ever heard of that. Codoc is a new documentation tool coming out. Extension points and module aliases are new language features that have made a lot of this tooling natural and easier and all that. And so there's a kind of a mix, which is to say, it surely hurts, right? It's nice to get Visual Studio. Visual Studio is pretty good. Like, lots and lots of work has gone into making Visual Studio effective. Eclipse has had lots and lots of work in it, although it still, in some ways, sucks. But still, there's a lot of benefit you get from the development tools and from the libraries and all that. And I think one of the things that you inherit when you use a minority language is, so you break it, you bought it, right? Like you've gone and used some weird technology that not everyone uses, and you were really successful, and like you are now kind of responsible, like for your own self-interest in maintaining this and helping it grow. And that's the position we're in, and I think all in, I'm very happy with the trade. But it's not a trivial one. So I'm basically out of time. I'm like a minute over. Let me entertain a question or two, and then people can hang around after, but I'll let everyone else go after that.
So why don't you think more firms either use OCaml or use some programming language that's not very common?
So it's a good question. I think one background piece of information is that programming languages, for reasons I don't totally understand, in general move incredibly slowly and irrationally. So a great example is garbage collection. That's a pretty good idea, right? Probably the single best idea for improving programmer productivity in the history of in the history of programming languages. How old is that idea? It was invented in 1958. It hit the mainstream in 95 with Java. Why? I don't know. Yeah, it took a while to get efficient enough, so there's some technological things that have to be worked out, but mostly, people seem to act in deeply irrational ways when picking their tools, right? And I don't totally know how to explain it. Some of it is no doubt network effects that create inertia in organizations. Like, if you showed me a new language that was better than OCaml to switch to, it would have to be better by a lot. Like, we have several million lines of code in OCaml and lots of understanding about the details of the language, and switching to a new thing is really hard, and it has to be better by a lot. But that's one barrier that's surely there. I think also people get deeply emotional and somewhat irrational about their tools. I'm sure I do it as well. But the tools that you use, in some ways, they kind of form the way you think about and approach problems in a way that people get almost offended when they're asked to use some tool that's not their regular tool. And they get more offended the longer they've been using some other thing. So I think that also, I think, has something to do with it, but it's a complicated question. I think progress in programming languages is really, shockingly so. Again, garbage collection was a good 35 years. Generics, which showed up in Java, also a similar time. Type inference, similar time. They're all landing. C# now has local type inference. Yay! 35 years late. It's a little hard to figure out. You could imagine, well, maybe the differences are kind of small, so they don't matter. I don't think that's true, but it's incredibly hard to study. That's another thing that goes into it. You may think, why don't people do research studies showing how much languages affect people's productivity? It's great. Are you want to be in the group randomized into using COBOL for the next 20 years of your career? Right? And you need a long time because the only experimental tool you have in a university is sophomores. Right? Those are the guys you have at hand. You can do lots of studies with sophomores, but you cannot construct a pile of sophomores high enough to get anywhere on this problem. Because programming languages are professional tools. And what matters about how they're effective is how they're effective, over, a long time. You're going to have a 20, 30-year career doing this stuff. Your first 2 weeks doesn't matter, but that's all they can measure, right? And it doesn't matter what you do in the 16-line program you write. It matters in the million-line project that you collaborate on with lots of people. And they can't, there isn't any way of running reasonable studies about this. So it's a place where it's very hard to convince people, and it's so much emotion in the topic that it's not clear what to do.
Other trading companies or companies you've heard of use OCaml?
So I don't know of any other firm that uses it kind of in the both hands and both feet all the way that we do it. Facebook uses OCaml these days. They wrote a compiler called Hack and another one called Flow, which are compilers which, the point of these compilers is actually they essentially add the ability to have a type system to languages like PHP and JavaScript, respectively. There's a kind of general kind of trend in computer science of lots of energy going into putting lipstick on pigs, and the PHP pig has had a lot of lipstick from Facebook. But that is a big system, a fairly significant team working on it, 40 or so developers, all in OCaml. A very high performance system, amusingly. So this goes to like, so in Facebook's kind of developer kind of organization, you can't get people to use tools by telling them. You have to convince people that they want to use the tools. And so these PHP programmers aren't used to compilers. So you had to give them a world that felt like there was no compiler. So they wrote a really high-speed reactive compiler that like traces down dependencies down to the function level and watches the file system for changes. So you can like use a source code tool like Git and do a Git rebase that changes thousands of files. And the compiler is just kind of noticing everything and running along. And the compilation is finished 20 milliseconds after Git is done, which means the compiler is running significantly faster than Git can change the file system. So this is an interesting bit of technology. Bloomberg uses OCaml for a bunch of stuff. The guys at Twitter use Scala, which is a closely related language. They actually considered using OCaml, but decided the JVM was too valuable for some of the kind of reasons I talked about. There are some smaller places using Facebook uses Haskell, which is another related language for some bits of their infrastructure. So there are definitely places in the world, other places that use it, and there are lots of financial firms that use Haskell for fairly different businesses than the one that we're in. And F#, another similar language, shows up. But like, I can point to lots of other examples, but they're kind of grains of sand in a large sea of not using it. I still think that statically typed functional languages like OCaml are increasingly talked about and increasingly taught, but they are more talked about than used. Okay, so let's break and people can go, and I'm happy to stick around and chat if people have other things they want to ask, but thank you.